In Lesson 4 of our Serverless LLMs and Agentic AI course, we're going to explore how hardware choices and resource reservations affect real AI inference performance on Modal. Instead of running a toy function, we'll build a small but realistic embedding microservice, a service that takes text input and returns a vector embedding using a lightweight transformer model. This is one of the most common building blocks in modern LLM systems because embeddings power things like semantic search, retrieval augmented generation, clustering deduplication, and even routing requests to the right tools or agents. The main goal of this lesson is to run the exact same embedding workload in 3 different modes and compare the results, first on CPU with default resources, then on CPU again but with explicit reserved CPU cores and memory, and finally on a GPU using an A10G by default to see how much throughput improves when model inference is accelerated. Along the way, you'll learn how to request a GPU for a modal function, how to reserve minimum compute and memory using CPU and memory, how to measure throughput in requests per second, and how to debug a GPU container the same way you would in production by opening a modal shell and running tools like nvidia-smi to confirm GPU availability and utilization. Before we do anything with GPUs or resource reservations, we first need to make sure Modal is installed and available in our environment. In this step, we install the Modal Python package using pip, which gives us access to both the Python SDK and the Modal command line interface. After installation, we verify that the Modal executable is on the system path and print its version to confirm everything is set up correctly. If you see a valid path and a version number in the output, it means Modal is installed and ready, and we can safely move on to running GPU-enabled functions and reserving CPU and memory in Lesson 4. Before we can run any code on Modal's infrastructure, especially GPU-backed workloads, we need to make sure our environment is properly authenticated. Modal uses API tokens to securely associate this notebook or machine with your account. In this step, we configure authentication using the Modal CLI by calling Modal token set with a token ID and token secret that you generate from the Modal dashboard. When this command runs, Modal stores the credentials locally in its configuration file, so future commands and notebook cells can communicate with the Modal backend without any extra setup. The small safety check in the code prevents the cell from running if placeholder values are still present. Once you see the confirmation message saying the token has been stored, it means authentication is complete and we're ready to start requesting CPUs, memory, and GPUs for our embedding microservice in Lesson 4. In Step 2, we set up the entire project we'll use throughout Lesson 4 by exporting our code into a standalone Python script called lesson4_gpu_resources.py. This script defines a small embedding microservice with 3 different modal functions that all run the same embedding workload, but with different resource configurations so we can compare performance fairly. First, embed_CPU_default runs on CPU using Modal's default resources, giving us a baseline. Second, embed_CPU_reserved runs the exact same logic, but requests guaranteed resources like CPU equals 4 and memory equals 2048 megabytes, so we can see what happens when we reserve minimum compute and memory for more predictable throughput. Third, embed_GPU runs the same model on a GPU by requesting GPU equals A10G, which is a common and cost-effective GPU option for inference workloads. Inside the script, we define a custom modal image that installs all required libraries inside the container, including PyTorch and Hugging Face transformers, so the remote environment has everything needed for model inference. The workload is based on a well-known small embedding model, sentence transformers /all-mini-lm-l6-v2, We load the tokenizer and model inside the container, build a batch of sentences, tokenize them, and then repeatedly run the model forward pass while measuring the elapsed time. From that, we compute simple throughput metrics like total items processed and items per second, and we return the results as a plain Python dictionary. Returning a dictionary is intentional because it's portable. Your local machine or collab doesn't need any special libraries to deserialize it. Finally, we define a local entry point function, lesson 4_main, which uses simple Boolean flags like --run-GPU and --run-reserve-CPU to decide which benchmark to run. One key detail for students is that the first run often includes model download and container warmup, so it may be slower, but after that, Modal caches image layers and artifacts, making reruns much faster and closer to real production performance. In step 3, we run the CPU baseline version of our embedding microservice, which is the safest and simplest way to validate that everything is wired correctly before involving GPUs or reserved resources. This command executes the embed_CPU_default function, meaning Modal assigns the default CPU and memory resources and runs the embedding workload entirely on the CPU. On the very first run, you should expect it to be noticeably slower because Modal has to build the container image, install PyTorch and transformers, and download the embedding model from Hugging Face into the container. That setup cost is a one-time hit. When you run the same command a second time, Modal reuses cached image layers and the already downloaded model, so execution becomes much faster and closer to what you'd see in a steady-state production system. This baseline result is important because it gives you a reference point for throughput and latency, which will later compare against CPU runs with reserved resources and GPU-based inference to clearly see how each resource choice impacts performance. In step 4, we rerun the same embedding workload, but this time with reserved CPU and memory, which gives the function more predictable and often higher performance. By enabling the --run-reserve-CPU flag, we switch to the embed_CPU_reserve function, where Modal guarantees at least 4 CPU cores and 2048 megabytes of memory for the container. Unlike the default CPU mode, which may share resources with other workloads, reserved resources reduce contention and performance variance, making this setup closer to what you'd want for production inference services. You'll typically notice higher and more stable throughput, especially as batch size increases. This step demonstrates an important lesson. You don't always need GPUs to get meaningful speedups. Carefully reserving CPU and memory can already make a big difference for embedding models and other moderately heavy inference workloads. In step 5, we run the exact same embedding workload on a GPU, which is where serverless acceleration really shines for model inference. By passing the --run-GPU flag, Modal executes the embed_GPU function inside a container with an attached GPU, an A10G by default. The code automatically detects CUDA availability, moves the model and tensors to the GPU, and synchronizes properly to measure true execution time. With a larger batch size and more repeats, you should see a dramatic increase in items per second compared to both CPU runs, especially once the model is warmed up. You can push this further by switching the GPU type in the function decorator using L4 for cost-efficient inference or a 100 and H100 for maximum throughput. This experiment clearly shows when GPUs are worth the cost. High throughput, parallel inference workloads like embeddings, LLM serving, and agent pipelines. In step 3, CPU default, the job took 9.0368 seconds. This is Modal's baseline. No guaranteed CPU cores and no memory reservation. Your function is sharing resources with other workloads on the same host, which means lower and more variable performance. This mode is fine for correctness checks or very light workloads, but it's not ideal for consistent inference throughput. In step 4, CPU with reserved resources, the time drops to 4.3397 seconds. roughly 2 times faster than the default CPU run. By reserving CPU equals 4 and memory equals 2048, Modal guarantees that your container always has enough compute and RAM. This removes contention, reduces scheduling delays, and makes performance far more predictable, often the sweet spot for CPU-only production services. In Step 5, GPU, the same workload completes in just 0.6481 seconds, which is about 14 times faster than default CPU and approximately 6.7 times faster than reserved CPU. This is the payoff of GPU parallelism. Matrix operations and batched inference scale extremely well on GPUs. For embedding generation, LLM inference, and agent pipelines, this kind of speedup translates directly into higher throughput, lower latency, and better cost efficiency at scale. In Step 6, we learn how to debug a GPU-backed modal container, which is a critical skill when you start deploying real model services. Even if your code runs, you should still verify that the container truly has a GPU attached and that your framework, like PyTorch, can actually see and use it. The command modal shell lesson 4_GPU_resources.py: embed_GPU opens an interactive shell inside the exact container environment used by the embed_GPU function. Once you're inside, you can run nvidia-smi to confirm the GPU type, driver status, and current utilization, just like you would on a traditional GPU server. Then you can run a quick PyTorch check to verify CUDA availability and print the GPU name, which proves your code is correctly configured for GPU inference. This debugging workflow is extremely useful in production situations when performance looks suspicious when CUDA isn't detected.